About a year ago, I had the bright idea to recreate Bad Apple in Roblox using grid of studs. The example showcased in that project was not very promising. Instead of a smooth 30 frames per second, it came out closer to 3 frames per second. Obviously not what I was looking for. Additionally, its dimensions were only 26 by 20 pixels, creating a pixelated mess instead of a beautiful video that I hoped for. Lastly, the image was flipped and warped in some frames, issues I could not ignore. So, I reworked the original implementation into a smoother experience rendered at a full 30 frames per second. However, this implementation still had many issues. First, frame data. I had originally made a pretty stupid decision to export the frame data as individual JSON dictionaries. Each pixel had its own exaggerated index and detailed RGB coloring. This boilerplate information caused frame files to be much larger than necessary, and explained why it could only be rendered at such a low resolution. Additionally, the original project code was messy. Although I cleaned it up a bit for this video, it still was a jumbled mess of code, certainly not portfolio worthy. So, I decided to try again. Instead of using studs, this time I used Roblox's own voxel terrain engine to generate frames. The Roblox terrain engine, frankly, works in mysterious ways to me. I've never really touched it before, so I thought this would be a good introduction to the system and its subsequent APIs for me. To start this project, I need to first acquire some frame data for my terrain. Last year, I had used a jargled mix of Node.js and FFmpeg to export the terrain data, and this wasn't going to cut it. I still decided to use Node.js, because it's what I have the most experience with outside of Roblox, but professionally write my code this time. Before touching Node.js though, I need to first convert the video into individual frames. I was well aware before and after this project that there are ways to convert the video file straight into the results I was looking for, but those require the use of video buffers and more complicated implementations, so I decided to just export the video straight into frames. Also, isn't it just fun to scroll through all these frames? To export the frames, I use this command. It first takes an input the Bad Apple video, verifies it's in the correct dimensions, and then exports each frame and numbers it with the leading 0 for aesthetics. After running this command in a short wait, I was left with 6,573 frames, coming in at about 50 megabytes of data. Next was to convert each frame into pixel data. Now for this project, I wanted each frame to be as small as possible. You see, in my older attempt, I rendered the project at 26 by 20 pixels, or about a total of 520 pixels per frame. For this project, however, I instead had grander dreams and rendered this project at 192 by 144 pixels for a grand total of 27,648 pixels per frame. This dream led me to optimize pixel data storage in any way possible. Boilerplate information in pixel indices? Gone. Complicated color data? Gone. Per frame JSON decoding? Gone. Instead of storing 3 bytes, or about 24 bits per pixel, I'd only be storing 1 bit per pixel. 1 meaning the pixel is black, and 0 meaning the pixel is white. You may be asking yourself, why didn't I do this originally? And to be completely honest, I have absolutely no idea. See, my original attempt was more about learning FFmpeg and processing images than being efficient, although this is still a very large oversight. To be nice, the original more complicated system of storing an entire RGB value for each pixel did end up creating a more nicer pixel blend. Was it worth the cost though? Absolutely not. Now, let's write some code to convert the image data into terrain data. In the code, we first see packages and variables. See, for both projects, I had opted to use the package image_decode because it served my purpose extremely well, as it allowed me to easily generate an array of pixel colors in just a single line of code. Next, we define the directory for frames, the output directory for frame data, and the threshold for white pixels. After verifying the output directory exists, we read the entire directory of frames, filter for PNG images, and sort them. Then, in this data, we generate an array for each frame by first using image_decode to get pixel color data. Then, for each pixel, we identify each color channel, use some math to generate grayscale, and finally use an inline if statement to identify if the pixel is white or black. After repeating this for every pixel, we number the frame with leading zeros, again for ethical reasons, generate the full path for the frame, and finally convert the array data into a Lua module and write the file. Okay, 2 things to point out here. First, you may have noticed I am creating a file for each frame. This is because attempting to import the data all at once to Roblox crashes Roblox Studio. And again, isn't it fun to just scroll through these frames? Another thing is you may be wondering why I'm writing thousands of Lua files on my computer instead of in the game. Well, this is because I'm using Broho to sync my Visual Studio Code workspace to a demo game. Broho allows me to import every single frame in one click instead of spending hours copying over the data. Now that we have our trained data imported to Roblox, all we need is a way to visualize it. So first, I built a neon outline for where I wanted the trained data to be. Each frame would be 192 pixels wide, 144 pixels tall, all confined into this area. I also added a backdrop of just water to create some contrast. And finally, a bar to display the current frame number and show the right way to view the video. To render the frames, we first reference where the frames are, define the FPS, height, and width of the video, the size for each train voxel, in this case 4 studs, and an X and Y offset to center the display. Additionally, an adjustable height offset for the terrain and an easier accessible table of each frame to prevent lag with get children requests. Then, to draw the frames, I wrote a function that intakes the frame module as an instance, loads the frame data, loops over each pixel, gets its index and value in the data, and finally uses the fill block function to fill the pixel with the assigned terrain. For this demo, I use grass as the primary terrain and air as a secondary terrain, but I'll switch them around as I play the project to show each material's unique properties in this situation. Finally, we sort the frames list in the correct order by name and play each frame. You may think that it'd be easier just to loop over every frame and display it with a small cooldown like this, but unfortunately, that has its own issues. One of the main issues of the original attempt was the project's speed. See, trying to update hundreds of pixels in less than 1/30th of a second is absolutely insane and causes many issues. You could try to fix this by adding the update function to its own thread, but the issues persist. The tremendous lag caused by hundreds of updates slows down each frame to more of a slideshow than video. So instead, we fake it. Instead of relying on defined intervals, we first define the start time of the video and the current frame. Then we define a loop to continue playing until our current frame variable has reached the total number of frames. Inside this loop, we first calculate the elapsed time and which frame we should be on by multiplying the elapsed time by the video's frames per second and adding 1, because Lua tables start at 1. Then we make sure we haven't run out of frames and also we aren't already displaying the frame. We draw the frame for the terrain using the previously mentioned draw frame function and do a small wait to avoid script exhaustion. Finally, after running all this code and adding some cool countdown frames, we get this. I hope you've enjoyed watching this video, and if you'd like to test out the project yourself, you can view the source code on GitHub and download it using the instructions followed in the README, but without the frames for obvious reasons. If you have enjoyed, please subscribe or drop a like for more projects on Roblox like this, and comment what I should do next.